Let's start today's session. Today, week 6, we are discussing fluid mechanics. So, the topic today that will be discussed is related to flow between parallel plates and something about flow kinematics, something like stream function and velocity potential. Right? Okay, so first we'll start with the theory question.
GATE 2017, Set 1, question number 12. For a steady incompressible laminar flow between two infinite parallel stationary plates, the shear stress variation is A. Linear with zero value at the plate. So it will look like 0. B option will be, it may look like this. No. B option with a linear with zero value at the center. It will be like this. C is quadratic with zero value at the plate. So something like this. And D quadratic value with 0 at the center. Maybe like this or like this. You may try to remember the answer as it is, that is B, linear with 0 at the center. So of course we know that friction will be most where the stationary point is there, that is the wall, and less where there is the velocity is maximum. As we know, the velocity profile will come like this, a parabola with maximum on the center and minimum or zero at the stationary walls. So the shear stress that is given as tau is equal to nu du by dy will be maximum at the wall and zero at the center. But then whether it is linear or quadratic, that we have to identify. So for that, if you remember the formula for the steady state velocity, which was given as v is equal to minus 1 by 2 nu dp by dx d minus dy minus y square. So this is the formula for velocity when you are going from one plate to another. So y is equal to 0 is at this place and y is equal to d is at this place. So if you use this formula and actually try to calculate the shear stress profile using the standard equation, you will get something like a linear equation which is 0 at the center and maximum at the edges. So you see, this is your tau, that is 1 by minus 1 by 2 dp by dx d minus 2y. So when y is equal to d by 2, that is the center, tau is equal to 0. And whenever y is equal to 0 or y is equal to d, your tau is maximum. So the answer is B.
Let's go to next question. So these are some theory questions that we have to kind of remember from our experience when we are solving. But there are some fun questions which we are going to look at, where we get to do some calculation and get to some real answers. Okay, so the divergence of a vector. So this is also GATE 2017 set to question number 90. Sorry, I forgot to mention that. So the divergence of vector field. So here it is representing the velocity at x is equal to 1, 2, 3 is. See, in this case, the important thing is for you to remember what is the difference between divergence, right, gradient, and curl. So divergence is done for a vector to convert it into scalar. Gradient is done for a scalar, specifically a function, to convert it into vector. And curl is cross product basically for a vector to another vector, right? So if you know these things, then it is easier for you to solve this question. So let's say if V is a vector, divergence will be this divergence vector, which is d by dx I cap d by d by dy j cap and d by dx k cap. So divergence will be a dot product between this delta and v. Gradient will be, if this is f, this v is a vector and f is a function, which is function of x, y, and z, let's say. So, or instead of f, we say capital F is a function of x, y, z. So this is divergence. Gradient will be just a multiplication. So now you are differentiating this function with respect to x and keeping the resultant in the I cap, right? And then you are differentiating with respect to y, keeping the resultant in the j cap, and similarly you are doing for the k cap. And curl is the cross product. So that is also for a vector. So yeah, which will be a vector perpendicular to the f and delta. So the notation, it goes like this. I think we all know this, but just for completeness, I am writing it here. Vx, Vy, Vz. Okay. So if you know this question is pretty simple to solve. So if you want to take screenshot, you can take now, or you can take it from the video when it is uploaded in the channel. I'm going to erase this and we are going to solve this question. So when I was uh, editing the video and to upload in the YouTube channel, I heard that someone asked for the first question in the last session. So you can get it from the YouTube channel if you're joining late because we cannot. I don't want to go back, right? So if you are joining late, you can go back and see from this channel that we are required to make and upload all these live sessions into. Okay, yeah. So what to do in this question? We have been asked divergence for this vector field. What was divergence? Just a dot product and then converting to scale. So the differentiation of the component in I with x, the component in j with y, the component in k with z. So dy dx of x square is 2x plus dy dy of 2y cube is 6y square plus dy dz of z power 4 is 4z3. And then we put in the values and we have 2 plus 6 into 4 plus, sorry, 4 into 27. Right? So what is the answer? Can anyone tell me? And if you are getting any other answer, then also you can tell and we can figure out who's wrong. If it's not surprising, then I also can be wrong here. So I'm getting 134. Is everyone getting 134? Okay, I'm going to assume that everyone is getting 134. So Ajay wants to say something. Yes, Ajay, please. Oh, just a second. I don't know. I'm unable to hear you. Just a minute. Can you speak now? Okay. Okay, thank you, thank you. Okay, luckily, since you spoke, I was able to figure out that my headset was not working properly. So thank you for that also. Yeah, good. Okay, now we are coming to some interesting parts. So we are going to now thoroughly see many questions that have come from the stream function and the velocity potential. And I've seen that in government exams, simple questions will come, and then these simple questions, because we are not able to recall them, or these concepts are not in one place, it becomes a little bit tricky to keep them in mind. So I will try my best to cover these concepts, and we will see if it helps. Okay, so this question, stream function for a two-dimensional flow is given by psi is equal to 2xy. The velocity at 2 and 2 comma 2. So x is 2, y is 2. What is the velocity at this point? So to do this question, what do we have to remember? We have to remember few things. First, this is stream function. And what is this? This is velocity potential. Can we get velocity u component, v component by this stream function? Yes, we can get. How we can get? U is equal to minus d psi by dy. V is equal to d psi by dx. Similarly, can we get velocity using the velocity potential phi? Yes, we can get. U is equal to minus d phi by dx. V is equal to minus d phi by dy. Okay, so this is something which you can note. So if we use this, there are a lot more things to talk about these two. First, we'll solve this question, and probably for the next question, we are going to see some more concepts. So if we look at this question, u is going to be minus 2, sorry, minus 2x, and v is going to be 2y. Is everyone getting this? Okay, good. Then u will be minus 4 and v will be 4. So the resultant velocity, which is nothing but the magnitude of the velocity, is going to be root under u square plus v square. That will be 4 root under 2. So this is the answer. Simple enough question. But in exam, sometimes we get confused which one to use. So we have to remember, yeah, we have to remember only these kind of things. Or maybe if in the following points that I am about to say, maybe if it helps to distinguish between these two better, then let's see. Okay, so we have been given stream function, and we have been given velocity potential and the stream function. Given the velocity potential and the stream function, the discharge passing between the stream lines through the point 1, 3 and 3, 3 is, so there are 2 points, and we have 1, 3, and let's plot them here itself. So you can read the question by the time I'm trying to draw this, and if you have the answer, you can raise your hand and we'll let you tell the answer. So we have to tell what is the discharge passing between 1, 3 and 3, 3 given the stream function and the velocity potential. Now my question to you, do we need all the data that has been given in this question, or can we ignore some of the data and answer this question? Some of the information is redundant. That also, see, this is a classic example of the question which is given to you to confuse you. So the redundant information in this question is this velocity potential, because the discharge passing between 2 points in space can be calculated by the difference in their stream function value. So we can easily get our discharge by doing psi 2 minus psi 1. What is psi 2? Psi 2 is nothing but 3 by 2, 3 square, so 3 is there. 3 square minus 3 square 0 is 0. Psi 1 is nothing but 3 by 2. 3 square is 9 minus 1 square 1. So psi 1 is 3 by 4, 3 by 2 into 4, 8, so 12. So psi 2 minus psi 1 is going to give us 12. So actually it's the magnitude. So we'll take magnitude and we get the answer as 12. That is the answer. Now if you were to use this, if you were to get confused and you use this, let's see what we get, if we get any answer. So if we were to use phi 1, we will get 9. Phi 2, we will get 27. So 9 minus 27. So luckily I think in this case we are getting 18, which is not the answer, but they can actually modify this question in such a way that you can get an answer which is one of these options, and then you are stuck with this fear that which function should I use to calculate the discharge. Because what sticks with us is that we have to take the difference of the function value at 2 point, but what we tend to forget is which function value difference we have to actually take. So it is the stream function. Okay, now is this clear? We'll go to the next question then. Okay. Consider the following parameter related to fluid: vorticity, velocity potential, stream function. Which of these parameters exist both in rotational and irrotational? So this is a question where we can cover all the concepts related to all the useful concepts related to the stream function and the velocity potential. So here we have stream function and here we have velocity potential function. So earlier we saw that the velocity can be written as this. So we'll stick to the 2D because that's what is most commonly asked. Oh, sorry about this. So earlier we have seen that we can get the velocity from both of these functions by doing the proper derivative. Now, what is this equation, if I may ask? What is this equation called? What do you guys think this equation is? Euler's equation. What is the more commonly known name for this equation? Let me make it easier. Laplace equation is actually not the correct answer. Let me write this. Let's see if this gives you a hint. What do you think? Now, what do you think now? This is the correct. This is the full form. This is the continuity equation. Okay, so any flow, if there is a flow, it has to follow the continuity equation. When we say the flow is incompressible, that means the density doesn't change, then the equation gets in this form. And then when we talk about 2D flow, then the equation comes into this form. Okay, so since we are sticking to 2D flow, this is the equation that we have to remember, which is called as continuity equation. Now, if the flow has to exist, it has to follow the continuity equation. Now, look at this continuity equation carefully. Du by dx plus dv by dy, or dou u by dou x plus dou v by dou y equal to 0. If I substitute u from here, u and v from here, from the velocity potential, then what do we observe? We get dou square phi by dou x square minus dou square phi by dou y square is equal to 0. When you take out the minus sign common, we get this expression. Now, what is this expression? Someone has actually mentioned this earlier. This is the Laplace equation. Laplace equation. So, what we can say, if if the velocity potential follows the Laplace equation or the Laplace relation, then the flow exists. So what you will observe is so we'll have some questions. I'll try to frame some questions here itself, and we will see some of these, try to see whether they follow or this follows the Laplace equation. Okay, so yeah, that we'll see. Now this is a property Laplace equation for this velocity potential. So when we know that when the velocity potential follows the Laplace equation, flow exists. Does something special happens when stream function follows the Laplace equation? So we have to see. It actually does. And we kind of have to mug it up because it is not very pretty looking. So when we have this, that is stream function following the Laplace equation, then in that case flow is irrotational. There is no vorticity in the irrotational flow. So let me write here also the symbol. This is vorticity, which basically is equal to the cross product of our delta and the velocity vector. This is the velocity potential phi, and this is stream function psi. So when the stream function follows the Laplace equation, flow is irrotational, vorticity is 0. Okay, and only in this case, okay, so here's one more point. It may be too much information, but try to remember this. Only when the flow is irrotational, only when the flow is irrotational, that is only when your vorticity is 0, does your velocity potential exist. If vorticity is not is equal to 0, your flow will exist. This velocity potential will not exist. Okay, that is when you have a rotational flow, that means flow is existing, then in that case your velocity potential will not exist. Kind of mugging up information, but we have to remember this. For rotational flow, phi doesn't exist. Now look at this expression. Sometimes you may not be given the Laplace equation for the in terms of stream function. Sometimes it may be given in some other way. So we'll try to see if we can write this in this form, in form of velocity. Like we have continuity equation. We'll try to see what this equation becomes if we try to transform it in that form. Okay, so we have d psi d2 psi square by dx square. That means it is equal to dv by dx. And then we have d2 psi, d square psi, d2 psi by dy square. That is minus du by dy. And this is equal to 0. So if instead of stream function following the Laplace equation, you are given something like this, then also you can say that the flow is irrotational. Okay, so this is a pretty important slide related to all the theories. So if you can try to remember this, then it will be good. Okay, now using this information, let's try to answer the question. What have they asked? They have told that for out of the following parameters, which of these exist, not non-zero or zero, exist both in rotational flow and irrotational. So now I am waiting for you guys to answer this question. What do you think is the answer for this question? Someone is saying D, Shailene Hari. Shailene, I just now told then that when we have irrotational flow, then one of the things doesn't exist, right? So it cannot be all the three that exist. Just answer is here. If you look at this slide itself, the answer is here. Anyone else want to try? Okay, so I will ask this one by one. When we have irrotational flow, we have vorticity. Someone said, Pallavi said C. That is 1 and 3. That is the correct answer, right? Because simply one point we have to remember here, that when the flow is rotational, the velocity potential does not exist. Okay, the answer is C. Okay, so here let me still talk to you about this. Vorticity is non-zero when the flow is rotational, but it is zero and still existing. It is not something which cannot exist. It is zero at irrotational. Stream function, it doesn't have any problem. Whether it is rotational, it is irrotational, it will exist. But the velocity potential will not exist when the flow is rotational. Okay? Okay, let's go to the next question. Okay, so yeah, this is a big question. So let's see if we can solve this. So we have, when we talk about flow between two parallel plates, we get some velocity profile. So how the velocity, the profile or the velocity will vary when we go up the plate. it is very clear to us that since the viscous stress or the shear stress is very high in the side of the plates, near the plates, the velocity will be lower on this side and it will be maximum in the somewhere in the middle. So usually we say that it takes this kind of parabolic kind of shape, right? So this is the case. What what we do is usually we want to write the velocity in terms of average velocity. And when we do that, then the momentum calculation and the kinetic energy calculation, we want to use average velocity. So when we do that, we actually kind of miss some of the details because instead of doing the integration and properly calculating the momentum, we are doing something such a like u average square and then the area or the diameter, something like that. So to correct for that, people have determined some kind of correction factor for momentum calculation using the average velocity and for the kinetic energy calculation. So here, what we are going to do is we are going to calculate the momentum correction factor for all these four flow profiles. So these are the flow profiles where V is the average velocity and we have been given the velocity changing with the depth as a function of the average velocity, right? So we will calculate the momentum energy factor and you can then further easily calculate your what is that kinetic energy correction factor. So momentum correction factor, that is also denoted as beta, is nothing but your actual momentum u square dy, changing the y changing from 0 to d, the diameter or the depth or the distance between the two plates, divided by u average square into the d, right? So let's try. And what is the kinetic energy correction factor? It is alpha 0 to d u cube dy divided by u average cube d. So this is kinetic energy and this is momentum. So with this information, let's try to calculate. Okay, so here we have a velocity profile which is constant throughout the depth. And what was V? V was the average velocity. So if you look at beta here, you will have 0 to d v square dy by v square into d, which is nothing but 1 because v is here constant and only d will change from 0 to d. So we will get a beta 1, that is the momentum correction factor for this as 1. Now let's look at this second example. We have velocity that is changing with the depth. Now what we see here is that it is showing some kind of symmetry. All these three are actually showing some kind of symmetry with the center, right? So let's try to calculate our this expression beta only for the half, and it will be same for the other portion also, and we don't have to do the full calculation. So we can do y changing from center to dy 2, from center to away. For that we need actually the velocity as a function of depth. So can you guys write what is the velocity as a function of depth in this case? It is maximum. So it is linear. You don't have to assume any quadratic or any polynomial. It is linear. So it is 1.25 v at the center and it goes to 0.0 0.75v. So what is the difference here? The difference in between these two is of 0.5, and then that difference is achieved in d by 2. So we can write this as y by d. Correct? So when y reaches d by 2, we have uh, the velocity as this. Is this correct, or am I missing something? Can anyone confirm with me? Is everyone listening? I don't know. Okay, let me myself correct it. So we have at y is equal to d by 2, 1.25 minus 0.5 into v into d by 2. So by 2 is remaining with us. So we have 1.25 minus 0.25, we have 1. So it is not correct, right? We just have to put values, and we can see that it doesn't seem to be correct. So what we have to do to correct it? We have to do 1.5v minus v y by d. So now if you put 1.5v y is equal to 0 from the center, you have 1.5v. When you go away from the center, d by 2, v d by 2d, and you see here it is 1.25 v minus 0.5v, which is 0.75 v. This is the correct expression. Is everyone following now? Okay, I am going to assume that you are following now. So similarly, can we get the expression for the other three before we go before we move on? Okay, some messages I am getting. Just a minute. Let me check the message. By the time I am checking this, I can you please try to get the thing for the velocity profile for these two? Simply use this and try to get it. And you can raise your hand if you have any doubt, and we can work it out together. Okay, so let me write the expression. We have 1.5v minus 2v y by d, and we have 2v minus 4 y by d into v. This is the expression. Are you all getting this? Oh, okay. So I think today everyone is a little sleepy. So let's I will solve this equation and let's see what we get in the end. So 0 to d by 2, we want to go for our y, and the expression is 1.5 minus, so we'll take v square outside, and we have anyhow v square d in the denominator. So since we are doing only the half, so we have actually v square d by 2 in the denominator, and this is the expression. This is the square here, and beta 3 will be 0 to d by 2, similar like this, 1.5 minus 2 y by d square. Then v square actually we can cancel out for the rest of the thing, and so this is also v, sorry, yeah, yeah, and we can keep this d here, right, and d by 2 here, and beta 3 or beta 4 will be 0 to d by 2, 2 minus 4y by d square dy, and d by 2. Let me check if my d by 2 is correct. Yep. So now we just have to do the integration and we can get our answer. So let's do the first one, that is beta 2. What's this? Beta 2 was d by 2, 0 to d by 2, 1.5, 1.25 minus y by d square dy. So basically 2 times of that. So we have 1.25 square plus y by d square minus 2.5 y by d. Okay, and this is going from 0 to d by 2. Sorry, first we have to do the integration also. My bad. We have to do the integration also here. 0 to d, 0 to d by 2. So the integration will give us 1.25 square into d by 2 plus v square integration is going to give us v cube by 3. So 1 by d square, v cube by 3, d cube by 8, that is d by 2 cube, minus 2.5 into d y square, which will be d by 2 square, d square by 4. So we'll have 2 into 1.25 square by 2 plus 1 by 8 minus 2.5 by 4 into d, which again got cancelled from the d in the denominator. So we can ignore this. So what is the answer now for this? 1.25 square divided by 2 plus 1 by 8 minus 25 by 4. Oh, sorry, 2.5 by 4. We have 0.5625 beta 2. Is this clear how we are getting this? Similarly, we can get beta 3 and beta 4. Okay, so I don't think that me just sitting here doing and this is going to be of any use. I'll leave it up to you guys to calculate beta 3 and beta 4. The concept is you have to follow this step and you are going to get your momentum correction factor. Yes. So since you have been silent till now, I want you guys to ask some question. Okay, yeah, we can do one thing. Rather than doing this monotonous calculation, what we can do is I want you guys to tell me whether this expression for the remaining time of the session, for this expression 3 by 2 y square minus x square, does is the flow irrotational? Come on. So I want you guys to tell me this. Some constant y square minus x square. Okay, today everyone is very silent. So if irrotational, thank you, Miss Pallavi for answering. Finally, at least someone answered. So this is irrotational. Pallavi is saying, let's check. So if stream function follows the Laplace equation, then the flow is irrotational, right? So let's see this follows or not. D psi by dx minus 2kx d2 psi by dx square minus 2k d psi by dy 2ky d psi by dx, sorry, d2 psi by dy square, that is 2k. So the sum of these two is going to be 0. So this means this flow is irrotational. And that is why we have psi, because if this flow was rotational, means if uh, the stream function didn't follow the Laplace equation, then we wouldn't have a feasible or a real value or a real function describing the velocity potential. So since now Pallavi has answered, forgive me Pallavi, but I want to drag you into this. Did you understand this? How to calculate the momentum correction factor? Which equation, Pallavi? Velocity profile. Okay, okay. Let's try to do that. Thank you. Yeah, thank you for asking this question, and let's try to do this. So there was, I think there was a mistake from where I was looking at this answer, so it made me confused. But hopefully, if we all can work together, we can identify the correct approach. See, this is velocity. This is the velocity profile. It is having some value in the center, 1.25 v, and some value at the edge. We want to get a relation which describes that that it is maximum 1.25 at the center and 0.75 v at the edge. Since it is symmetric, let's take this as our data and say this at this location y is 0 and at this location y is equal to d by 2. So basically what you have here is simple 2 point in a graph sheet where velocity, let's say y is x coordinate 0 and 1.25 v, and then you have d by 2. So I'm just going drawing arbitrarily, don't take this as the correct representation. D by 2 and 0.75 v, and now you have to get the velocity variable as a function of y. So you can see here, either you can do this, either you can use a y equal to mx plus c concept and get m and c, or either you can do this y minus equating the slopes. If you all remember that we have 2 points on the straight line, then the slope between these two is going to be equal between these two. So y2, y1, y2, and let's say this is y, and this is x, x2, x1. So y minus x2, y minus y2 1.25 v by x minus x2, that is 0, is going to be equal to y2 minus y1 divided by x2 minus x1. So if you solve this expression, you are going to get y is equal to 1.5 v plus x into 1.5 minus 0.75, 1.25 minus 0.75 is 0.5, and into d by 2 minus d by 2, that is 1 minus 1 d by, sorry, so am I missing something? So d will be in the denominator, and that by 2 is going to be above, which is multiplied with 0.5 to give us minus 1. Yeah, forgive me for that. Yeah. So did you get this, Pallavi? Similarly, so this is the expression that I wrote for that point. Similarly, you can get for this. So can you try to get this? So for the reference, I will write here. So we will have here v is equal to 1.5 v minus what is this? This one, so 2 y by d, and here we will have v is equal to 2v minus 4y by d. What shortcut you can use, since this is a very nicely framed question, what shortcut which you can use, but I will suggest that you use this shortcut only after getting comfortable with this approach. The shortcut is that you are going from 1.5 to 0.5, right? That, and so the difference between these two is 0.5, but you are achieving this difference in d by 2. So the equation finally, so you have some rough idea of the equation. The equation is going to be y is equal to 1.25 v minus some constant into y by d, because y is going to take the value from 0 to d by 2. So for the dimensionality, y is going to be divided by d in this equation, and it will be multiplied with some constant. You have you just get the idea that the equation is going to be something like this, right? So if the equation is something like this, then you see that what should be the value of k, that at y is equal to d by 2, my answer comes out to be 0.5. So then you see that when you put y equal to d by 2, this becomes 2k, 1.5 minus 2k. So the difference, this has to come out to be, so this will multiply by v, sorry, I forgot that. This has to come out to be 0.75. So 2k is going to be 1.5 minus, sorry, oh my god, I made a mistake again. So when you put y equal to d by 2, it will be k by 2. Yeah. So 1.25 minus k by 2 is coming out to be 0.75. And then k will come out to be 1. So similarly, you can see in this also that your expression is going to be 1.5 v. So I am going to take v constant, v out of the bracket for now, so that my life becomes easier. So the equation is going to be 1.5 minus some constant into y by d, right? So now again 1.5 minus d by 2, so k by 2 is equal to 0.5. This goes here, becomes 1, k becomes 2. So we have the equation 1.5 minus 2y by d. Here we have 2 minus k into y by d. Again 2 minus k by 2 is equal to 0. K is equal to 4. So we have the equation 2 minus 4y by 2. Okay, this is how we get. So this is whole is multiplied by v. Yeah. So actually the book where I saw this solution, which it gave wrongly the answers. So this is the correct way. If also you have seen in some books this question solution, so this is how you do it correctly, and then you get the beta, that is the momentum correction factor, that I have already explained how to get a simple integration. Okay, now did you understand this correctly, Pallavi? And anyone else also? Everyone else also understood this? Thank you. Yeah, so if you ask me questions, then it also, kind of allows me to explain it to you in detail. Yeah, so using this, you can calculate beta 3 and beta 4. So if you have doubt in any other question, this is very important. You can note this. If you can note this, you can take screenshot, or you can go back and check in the video that I will upload again and again. Try to refresh this. It will be for your benefit. And this is, yeah. So if you don't have any other doubt, then we'll end the session for today. Thank you. And thank you especially to Pallavi.